Here we go. Yeah, thank you. And thank you for Rebecca as well for actually helping to introduce some of the things I'm going to say, so that's really useful. I'm going to talk to you about our work in developing and delivering cassava with resistance to cassava brown streak and nutritional enhancement. So the relevance of the connection with synchrotron work and our collaboration with Arthur is going to come at the very end. So please hold on with me. I will get to that part. But what you're going to hear about, especially about the brown streak resistance component, if we want to deploy the nutritionally enhanced products with elevated iron and zinc, we're going to have to go through all of the processes that I'm going to describe for brown streak. And if we want to develop and deploy these to farmers, in my opinion, and most people, we're going to have to stack these. It's really hard to deploy biofortified products to farmers if there is, first of all, you have to convince them about the value of that, and if there's any yield penalty for the biofortification, it will not be accepted. So you need to stack it with something that's really important that the farmers are going to pick up. And as you will see, cassava brown streak is an example of that. Just quickly, for those of you who may not have heard about the Donald Danforth Plant Science Center, Arthur said that there may be some people who hadn't. The Donald Danforth Plant Science Center is based in St. Louis in Missouri. It is now the largest standalone not-for-profit plant science research center in the world. We have about 400 people based in this building just outside of St. Louis, with about 300 of those are directly engaged in research. So our mission is to improve the human condition through plant science, going to by feeding the hungry, improving human health, preserving and renewing the environment, something we heard of just from Rebecca, and then also enhancing the St. Louis region as a world center for plant science research. So part of the Danforth Plant Science Center is focused on Midwestern agriculture, which is pretty much corn and soy, but also for improving productivity and nutritional enhancement of food security crops. And our focus is in Africa. And these are the type of activities that we're engaged with in our international programs: product development, field testing, regulatory stewardship, deployment, capacity buildings, all things I'm going to tell you about through the project that I'm engaged with mostly, which is Arthur told us about VRCA. So for those of you, I'm really glad to hear, for the Brazilians who are here, you don't need to be introduced to cassava, mandioca, incredibly important crop. But of course, if you live in North America, cassava is not an important crop. But you can see here consumption per capita originated in Amazonia, spread to Africa, and now Africa is the central production for cassava. It's estimated to be consumed by about 800 million people on a daily basis, and after rice and maize is the most important source of dietary calories in the world. This is a really important crop. It has been identified as one of the most climate resilient crops that we have. It is not going to go away. It's going to get more important. And it's important for food security. I took this picture. There was a family living in this small hut, and this is cassava in front and maize in the background. Anything that impacts this was about quarter of an acre of food production for the woman and her family. Anything that reduces the productivity of this field will have an immediate impact on them and their health. So it's essential for food security, but also for economic development. At the local scale, women are processing cassava, making it into products, adding value and selling locally. But it's also developing, this is a photograph in Rwanda, a quite substantial industrial plant processing, buying the cassava from the local farmers and processing it, as we can see here, and selling it. A source of bioplastics and beer. Africa is the largest beer growing market, or market for beer in the world, and cassava can be an essential component of that, and to reduce wheat imports as well. many African countries spend a lot of money importing wheat. They could be using the cassava that they could grow themselves. So there are one of the major, anything that suppresses yields in cassava is going to be an issue, and one of the biggest factors in suppressing yields, and I'll show you especially in East and Central Africa, is cassava brown streak disease. This is the cassava storage roots. It's been sliced. You can see them here. This is, you'll get full value for these in the market. You could eat them, sell them to your family. This is what happens when you get cassava brown streak disease. Cassava brown streak disease is caused by the cassava brown streak virus and Ugandan cassava brown streak virus, two very closely related RNA viruses. They're transmitted by whiteflies. This plant was put in the ground as a stake cutting. 12 months later, this is what it looked like. You cannot eat this. You cannot sell it. You cannot give it to your family. And if you plant the stem cuttings for the next cycle, it'll be even worse. So this is a disaster. You can lose up to 100% of your yield due to this disease. It originated in coastal Eastern Africa, but is now moved over the last 20 years through Uganda, Rwanda into Central Africa. And the big worry is not if, it's when it's going to get to West Africa, because that is the most populated region in Africa and the largest cassava growing. Nigeria is the largest cassava growing country in the world. So it's going to get there. What's going to happen? So we need solutions. So we took we started our project called Virus-Resistant Cassava for Africa, and this is the Verka project that we heard of, and the goal here, our goal is to enhance the livelihood of smallholder farmers by delivering varieties genetically enhanced to resist virus diseases, in this case specifically cassava brown streak disease, and mineral nutrition, the biofortification part that I'll get to at the end, that we want to stack on top of the virus resistance. Because this is a GM product, and people always ask me at some point, so I would say now up front, there's no IP restriction to the end users for these products, and there will be no charge by the technology developers. But there will be the private sector involved. There has to be the private sector involved in getting this out. And I'll tell you about that at the end. By the private sector, I don't mean multinationals. I mean at the local scale, farmers selling enhanced cassava planting materials to other farmers. So our collaborators in Verka is the National Agricultural Research Systems in Kenya, Uganda, Rwanda, and Nigeria, shown here. We are a large multidisciplinary team. I can go into lots of details here, but these are the major areas that we're engaged in, because this is a product development and delivery project. It is not a research project. We need the science and technology, but we also need breeding, regulatory communications, capacity building, seed systems I'll tell you about, and then also building gender into this to make sure that we're reaching those people, women and youth, who will also benefit from the improved cassava products. So we're employing RNAi technology, which is a post-transcriptional gene silencing technology. This is a proven technology. It's been deployed, or it's been around since the late 1990s, and it's been deployed in papaya, plum, beans, squash, and other crops. So there's nothing new here. What's new is we're doing it in cassava. It's not been done before in this crop, and we're targeting a new virus, cassava brown streak viruses, and in Africa, in countries which have no experience doing this, no regulatory processes in place, or did not have when we started. So when you think about where we're starting from, we had to build the technology in cassava from the very beginning. How do you make transgenic cassava plants? How do you screen them? How do you analyze them? How do you field trial them? How do you do the regulatory? How do you do the communications? The project was involved in building all components of this, because it did not exist before we started. So I'm not going to go into lots and lots, very much detail here about how we made the plants. This is an inverted repeat construct where you have a big, strong promoter. You have sequences from the virus. The goal here is we're going to integrate sequences from the virus. We're going to make them transcribe double-stranded RNA, and that will trigger the inherent defense mechanisms in the plant. So it's a little bit like immunization. It's a little bit like the COVID vaccinations that we have. What we're doing is we are introducing little bits of the pathogen into the plant, in this case actually integrating it into the genome. That triggers the inherent resistance mechanisms. We're teaching the plant to recognize and arm itself against the pathogen before the pathogen actually arrives. So when the whiteflies inject the virus when they're feeding, the plant immediately recognizes it, chops it up. You don't get disease. That was the theory. That was what we were going for. We made a large number of transgenic plants at the Danforth Plant Science Center, about 400 of these, analyzed them, grew them up in the greenhouse, and then we inoculated them with Brown Street disease. And this is about 12 weeks after inoculation, and these are little storage roots which are made in the pots here. Cassava is a huge plant, so we can't grow them full size, but we can constrain them and grow them in small pots, just a few inches across, and they'll make storage roots about the size of my thumb. You pull them out after about 12 weeks and slice them up, and you can see them non-modified here. All the storage roots here have Brown Street disease in them. These are example 3 of the 9 transgenic plants that we tested in the greenhouse at this time. No symptoms whatsoever. And if we do a PCR, we can't detect any virus. So we were very excited about this. First example of using RNAi GM technology to give resistance to Cassava Brown Street disease. So we did more experiments, but what I always say to people, you can do as many, experiments as you want in St. Louis, but this is not a field in Africa. So you've got to go to the field. And this is what we did, and I'll give you some timelines and show you how this process went. We planted this field, I think, in 2013. Grew them for a month, pulled out the storage roots after 12 months, and sliced up every root and assessed for disease. And you can see the whiteflies on this leaf. There's probably 1,000 whiteflies on that leaf. That's one leaf on one plant, and we had 3,000 plants. You walked into that field, the whiteflies fly up, and you breathe them in. It's actually a rather unpleasant place to be, and these whiteflies are transmitting the disease. So this is just to give you an idea of a scale, 3,000 plants, 10,000 roots, 50,000 data points. So we were doing this for pretty serious scale. Lots of data, we published this, but this kind of like sums it up. On the bottom here, non-modified plants, 95% loss. There's only about 5% of this would be edible. Above that, the RNAi plants, less than 2% loss. So around about up to a 20-fold increase in usable yield, which is pretty dramatic. Most biotech products, if you could get a 3 or 4% increase in yield, you'd be extremely happy and pushing ahead of making a product. So again, in the field, we did this in Uganda and in Kenya, and it worked very well in both places. So this was extremely exciting for us, and encouraged us to go forward into a full product development and deployment pipeline. We started this in 2008. The idea we had 2008, let's go and do this. Let's apply this technology to cassava. We're still working on this. So this is, for those of you who may have seen something like this before, this is kind of a classic biotech product development pipeline and the things that you have to do. And we had this piece here. This is all our kind of research and proof of concept components here, 2009 to 14, sorting out the IP, making the constructs, making the plants I've described, and then getting to the field. We've been through multiple field trials in multiple locations. We've gone through a breeding program. And regulatory, I'll talk to you about that in just a second. And then this is where we are today. We're in national performance trials in Kenya. So we haven't deployed yet. The average time for a GM pipeline from inception to deployment is about 13 years, 12 to 13 years. So we're not far away. Actually, it's not out of scale with what would be expected. And as I said, every single step of this process had not been done before, so we had to create it. So obviously we want to get there, we want to get these to the farmers, but we're still working on it. We carried out our regulatory field trials because this is a GM product. We did that in, this is western Uganda, close to where you would go and see the gorillas, which would be around about here. And also in a field location close to Nairobi. We have other sites as far away as Mombasa and elsewhere in Uganda as well. And we followed the standard international guidelines, did compositional analysis. If you want to do this, we actually analyzed 100 components. Things like all the amino acids, all the minerals. This is what you need to do if you want to go through and develop an application for a GM product. So we submitted this in 2020 and we got a regulatory approval from the National Biosafety Authority in Kenya. It's June of 2021. And they approved what we're calling Event 4046 and the progeny thereof was food as safer food feed in the environment. And this then allowed us to go on and go into national performance trials. I have this piece in the middle here because this indicates the interaction that we've had, and I believe the next slide, I'll come back to one minute. We had to engage with the stakeholders, that's parliamentarians, farmer groups, religious groups, multiple people all the way through this. So over 5,000 stakeholders were engaged in this process, so it's as transparent as we can be. We then went through our breeding programs where we took our best line, we crossed that. This is our RNAi line. We crossed that with farmer-preferred varieties from Uganda because we wanted to bring in other traits that the farmers would want, not just resistance to disease, but all the other traits. Generated about 8,000 seedlings. They go in the field, and then you screen them, and then you just go through what a traditional breeding program for cassava would be. You start off with one plant. You put them in the ground, and you screen them. You don't do back-crossing. Cassava is like crossing dogs, people, horses. You get inbreeding depression. It's highly heterozygous. So you make one cross, you make as many individuals as you can, you put them in the field, and you screen them initially for simple things like disease resistance, root weight. The next cycle, but the next year, you look at more things, you keep multiplying your plants, you go to bigger and bigger plots. Eventually, you end up in multi-locational trials in different countries. And then you assess everything that the farmers would want. You end up picking your best. So we've done more than 30 field trials now, 7 locations in East Africa, and there's lots and lots of data. But this is the story. This is very similar to the plant I showed you at the beginning. This was the starting variety. This has been in the ground close to Mombasa for 12 months. This is one of our products, an RNAi line, one of the progeny of the original transgenic event. This has been in the field for 5 consecutive years. There is no symptoms whatsoever across over 100 of these plants in the field. We're doing the molecular analysis now to see if there's any virus in there, but we don't believe that there will be. There hasn't been when we've looked in the past. So the technology really works. It really works well. We've now combined this into very high-yielding varieties. It's durable across a wide agroecological range, whether we're doing this in Uganda or all the way down to the coast. That's really important for us. And gives us confidence that this product will have durability, and we can deploy it in a wide range of countries if they have the regulatory processes in place. Just a tiny bit of data. I don't know that you need data. You don't need stats for sure to show that, but this would be The mean score, we score in the field very quickly. You just score visually. This is a score of 1, no symptoms. This is a score of 5, the worst possible, you can't eat it. And these are the best local variety here. All of our varieties are significantly outperform them, whilst they yield just as well or better. I've already talked about this as our continued interaction, connection with the stakeholders, and this is a really important component of what we've done. This has now allowed us to move forward and take 8 of these lines to plant them in national performance trials across 7 sites in Kenya, and these are the last steps will allow us, we hope, the goal is to submit for variety of registration in 2025. We'll hopefully then get commercial release from the National Biosafety Authority, and then we can release to farmers. So how are we going to do that? So all of what we've described, if we go back to the very beginning, my expertise, and Arthur mentioned this, is how do you take a piece of DNA and integrate it into a plant cell and get a plant back? That's how I started. I'm a plant tissue culture biotechnologist. Now I'm interacting with breeders. Now I'm talking about selecting plants in multiple locations. The next thing that I learned was, it's obvious, but not until you realize it, there is no seed system in Kenya for dispersing quality approved cassava cuttings to farmers. So we're like, okay, we've got all of it. We have this material, which we believe is really fantastic. How are we going to get it out to 500,000 farmers? Cassava is planted at 10,000 stakes per hectare. So if you want to grow a hectare of cassava, you need 10,000 stakes. That is a lot. And these are not small seeds. These are stakes, as you can see, bundles of stem cuttings. Each one of those stems would be cut into about 6 or 7 pieces and planted. So there is no seed system, so we will not be able to get our enhanced planting material to the farmers. We will not have the penetration we need. Therefore, we have to build up the seed systems, and that's what we're doing here. We're training some farmers. These farmers, this is Mama Patience from Kilifi County near Mombasa, and she is being trained on how to grow quality-controlled, clean planting material. She will then sell these to the farmers. The farmers will grow it, and then the model is that they will come back and buy new cuttings from her and other seed entrepreneurs every few years. And this is a model that's actually been established in Tanzania for non-transgenic, and it works very well. So that's what we're building here and also in Rwanda. So now I want to move for the last few minutes onto the nutritional enhancement part. I don't need to introduce this because Rebecca already has, but what is interesting here is if you look at these 2 maps, this is the severity of hidden hunger, micronutrient deficiency pretty much overlaps where you grow cassava. So you would think, wow, if we could enhance biofortified cassava with iron and zinc and deploy that, we could actually reach many of the people who are, especially women and children, who are suffering from mineral malnutrition. So this was another of our goals. And our goal here was to pump more iron and zinc into the roots and then store that in the storage roots. And this is actually quite challenging because obviously all cells, all living organisms need iron and zinc and other heavy metals, but too much of them is toxic. So they have built very sophisticated ways of controlling that. So it's very easy to pump more iron, for example, into a plant cell, but you will kill it really quickly. So you've got to store it somewhere. You've got to sequester it and store it. And that's what we're doing here, where we took 2 genes. Was a major iron transporter, which will increase pumping of iron into the cell of the roots. And then we're going to store that using ferritin in the chloroplast. So we went ahead and did that, and this is some of the results that we got. Cassava storage roots have very little iron and zinc in them. Less than, it's about 7 to 10 parts per million maximum. And we talked about different genotypes having different amounts in cassava. We haven't seen that. They just don't. They're a really great source of carbohydrates. some vitamin C, but otherwise than that, you will not get your minerals. So when we made our transgenics in dark, in the black ones, you have our wild type controls, non-modified, and these are the plant lines that we've modified. For iron, we can now reach 9 times, up to 90 parts per million, and for zinc, we can reach up to 100 parts per million for zinc. So, so this is the part then. Once we had these, we were doing ICP analysis, but we wanted to visualize this. We wanted to have real proof that, hey, are we accumulating iron and zinc? And this is where we made contact with Arthur and his team here at Chess. And we did sectioning. These, again, are stem and storage roots from the greenhouse. These are not big roots. But we can see here co-localization of the iron and zinc in the storage root. This is the wild type, very little. This is the modified, is strongest in the center because a cassava storage root grows a little bit like a tree trunk. So the tissue in the middle is the oldest, so therefore it has been expressing and accumulating for the longest. So this was really important for us for verification that we were being successful. Where was it? We did not want it to be in the peel, because the peel is taken off and thrown away. So if it was going in the peel, well, then that would be wasted. We know it's not. It's in what's called the xylem parenchyma, this part of the root, the center of the root, which is the part that's eaten. Importantly for us as well, by working with Arthur and people here at Chess, this allowed us to get work published in Nature Biotechnology. So publishing in the highest level is not our goal is to deploy improvement planting material to farmers, but elevating this work and getting it into a publication like Nature Biotechnology really helps us tell our story well. And I sincerely believe we couldn't have done that without the collaboration that we had here. So I'm going to jump this just says that this is the levels of iron and zinc that we're reaching have significance, and it's not just, hey, we've got more iron and zinc. If people were to eat these, they aren't because they're regulated and we haven't deployed them yet. It would satisfy the nutritional requirements of especially children and non-lactating, non-pregnant women. So some learnings to finish off with. The RNAi technology that I described against cassava brown streak disease, it really works. We believe that now, so I'm now showing you that. We have 16 potential new varieties being developed, which can go into national performance trials. We have a projected product launch in 2025, and we're developing the seed systems to do that. What we've done as well, and I should have made more clear, is we've stacked. By that I mean we've taken plants with the RNAi technology, and we put iron and zinc biofortification on top of that. And this is our goal for deploying in Nigeria, and our plants are now under field trial in Nigeria to see how they perform in those environments, because I said at the beginning, I believe we need the brown streak resistance in order to convince the farmers to pick up the biofortification. And with that, I'd like to finish. There's obviously a large team, not just me, including, I love this picture because we mustn't forget the people who work in the fields, and it's really, really hot in these fields, and they were amazing. A large team who were involved in this, and our funders as well, the Bill and Melinda Gates Foundation, USAID, and we also had funding from Bayer. Thank you.